All right, welcome viewers. Today we are going to continue Unit 1, discussing some properties of functions. At the top here it goes over what intercepts are. Hopefully we know what intercepts are, x and y intercepts. Let's take a look at the graph here. And again, anything you want to pause and read through, feel free to go right ahead. So for A, what are the x and y intercepts? Well, the x-intercepts are, it looks like -6, 0, and -3, 0. There's no intercept at this hole here. And we've got a y-intercept at 0, -6. All right, so for B, we do not have a graph, we've got an equation. So to figure out the y-intercept, when x equals 0, we're going to plug in 0 for x and see what we get for y. So -2, 0 squared plus 2 times 0 plus 24. Great. So that should give us 24. I don't like writing two equal signs in one equation, but I'm running out of room here. So that point is at 0, 24. And the x-intercept when y equals 0, well, now we are plugging in 0 for y and seeing what we get for x. It looks like we are going to have to factor. So let's first pull out a -2. If the leading coefficient's negative, I like to pull out the negative. You don't really have to, but so we get x squared. This becomes a -x, and this becomes a -12. Hope I don't make any mistakes because I don't have any of you guys here to tell me I'm making mistakes. All right, I am running out of room, so I'm going to see if this can be factored. 0 equals -2. You know what? I'm not going to do that there. I am going to put an arrow, line, start here. And factor. All right. So I'm going to go ahead and just place my x's. And this has got to be a minus plus, or you can write plus minus, whichever one you see fit. Doesn't matter which factor goes first in that binomial. And that works because we have, check your factoring, always check your factoring. I make errors in factoring as well. So my x values, using the zero product property, are at -3 and 4. So those ordered pairs would be -3, 0, and 4, 0. All right, so we're going to discuss whether a function is even or odd. All right, so basically it has to do with the symmetry of the graph. A function is even if the graph is symmetric with respect to the x-axis. So here is, with respect to, even with respect to the y-axis. So here's the y-axis right here. And if you can reflect one side over the other side, and it looks exactly the same on both sides, you've got symmetry with respect to the y-axis. That function is even. For an odd function, it's a little bit trickier to see. The graph is symmetric with respect to the origin. So if you remember rotations back from geometry, if you plug in a +3 and you get a +3 value here, if you plug in a -3, you end up with a -3 here. So here's an example of a graph that's neither even nor odd, because it's neither symmetric with respect to the y-axis, nor is it symmetric with respect to the origin. So now we're going to do a test and see if functions are even or odd. So first you'll find f of -x, and then if that ends up having the same sign as the original function f of x, then the function is even. If the sign ends up being opposite, then it's odd. So for first three examples, you might want to pause and write this down or look at it. When you plug in for A, if I'm trying to find -x, I have to plug in -x into the quantity squared, because I have to square the entire -x, including the negative. And negative times a negative makes this a positive x squared, -5. So you see, x squared minus 5, x squared minus 5, they're the same, so that function is even. Now when I plug a -x here, in for B, I have to cube it, and then there's a negative weighting in front as well, which keeps this positive x cubed. This is a positive x cubed plus 1, but the original function is negative x cubed, and it's plus 1. So the sign of the entire function has not changed, just the sign of one term. So it's neither even nor odd. And C is an example of an odd function. So when you plug in a negative x, you end up with, you see how both the signs for the entire, both terms have changed here. So we have negative 5x squared plus 5x. And the original is a plus 5x and a minus 3x. Those, if you just distribute a negative through the entire expression here, you end up with opposite signs. So those are odd. So go ahead and pause and try the next two problems. And then I'll show you the answers. Okay, so again, you're plugging in negative x, and the sign for A is the same, so it's even, and the sign for B is, let's see, what changes in B? Oh, negative x cubed becomes positive x cubed, but then the sign doesn't change, so we don't even have to look any further. We can say it's neither. All right, when looking at the graph, just in summary, a function is even if it's symmetric about the y-axis, and it's odd if it's symmetric about the origin. So now we're going to go into increasing and decreasing. And again, you have seen this before last year, but a function is increasing if as the x values increase, the y values increase. A function is decreasing if as the x values increase, the y values decrease. It's a negative slope. And a function is constant if as the x values increase, the y values remain the same. It's got a slope of 0. So now we are just going to identify the intervals in these graphs where they're increasing and decreasing. So I'm going to go ahead and start here. That part of the graph is increasing. So it's from negative infinity, we always put parentheses around infinities and negative infinities, up to, but not including, negative 3. So I'm going to put a negative 3. It's not including negative 3 because there's a hole there. Let's see, the next section of the graph goes from negative 3 to 4, looks like. And we're going to include negative 3, and it's going to go to 4 and not include 4. But that has got a slope of 0, and that's a constant graph. So that's a negative 3 to 4. Usually when we're doing increasing and decreasing, just get comfortable with using parentheses and not hard brackets, because it has to do with the slope at the point of the tangent line, and you'll get into that next year. All right, and this part of the graph is decreasing, so that goes from 4 to infinity. Now again, you could, in a different color, you could look at these and make a case for hard brackets there because the slope of the tangent line, but I'm not going to go into explaining that. So, all right, so increasing, let's do increasing first. I like doing increasing first, right here. Looks like it's going from, is that negative 1 to 2? Okay, so from negative 1 to 2. I don't see any constant. And decreasing, we've got two parts, so we're going to have to go from negative infinity to negative 1. And there's your first, in union with the second part in red. Here's the second part, which goes that direction. So let's see, 2 x values that we're looking at here in the domain to infinity. There we go. All right, now if you have printed the keys, you might see other problems that I have decided to shorten these notes, and it's fine. Just don't worry if you see extra problems. It's not the end of the world. All right, so we're going to talk about a local or relative maximum minimum. So a local maximum occurs when the graph changes from increasing to decreasing. So here it's increasing, and then all of a sudden it's decreasing. There's your local maximum. A local minimum occurs when the graph changes from decreasing to increasing. Okay, so there's your minimum. Those are two more examples. So we're going to go ahead and I'm going to label this graph. Well, I already have the answers here. So for when they ask you a question, and I'm not going to be tricky about this on quizzes or tests or anything, but it is something for you to know. When they ask you, where does the function have a local minimum, they're asking for the x value. And when they're asking what is the local minimum, they're asking for the y value. So for A, if you're looking for the local maximum, all right, here's the maximum. A is asking for the x coordinate of that point, and B is asking for the y coordinate. So see if you can go ahead and do those problems for A, answer those questions for A and for B. And then where does the function have a local minimum? Okay, well, minimum in green is going to be down here. All right, now for B, we've got we see the maximum up here, but then looks like we've got a minimum because it turns around, goes right back up, and then we've got another maximum. So we're going to have two maximums. So see if you can do those problems for practice, and then show you the answers. Check your answers. See if you have any questions on that. And again, if you've got questions, hold your questions and we can discuss them in class. It's not a problem at all. All right, so we're skipping C. If C is in your notes, you may or may not have it. We're not doing that problem. And we're going to move to the last part, which is finding the average rate of change. All right, I have 4 minutes. Okay, so if C is in the domain of a function of y equals f of x, and the average rate of change from f to c, from c of f from c to x is defined as, and now this is technically slope. Okay, we don't really call it slope anymore when we get to calculus. Okay, but it's average rate of change, so it's y2 minus y1 over x2 minus x1. It's the same formula you would see back in algebra 1 when you were finding the slope of a line. So when you're given a function, like in example 5 here, find the average rate of change of the function. I went ahead and plotted some points and graphed them. You're going to see if you pick any 2 points, you could draw a straight, oh, that's a terrible straight line. You could draw a straight line, which we call a secant line, right through those 2 points. In fact, I think I have a graph below this. Yes, this is from the calculus textbook. So you can pick any 2 points on your curve, and you can draw a line, and it's going to have a different slope. So that's why it's the average rate of change, because depending on what 2 points we pick, we're going to have a different slope. So they're saying find the average rate of change between these 2 particular points. So for A, we're going between 2 and 4. So all we need are, when the x values are 2 and 4, what are the y values? So you plug them into the equation, and here are your y values. So now we're just going to do y2 minus y1 over x2 minus x1, just like we do in slope. And that is exactly what that says. F of 4 is 8, because when we put in 4 into our equation for x, we get 8 for y. That's all that says. Okay, so I didn't finish the problem. So that's 8 minus 2 over 2, so that's 3. So that's the slope of a line containing those 2 points. There you go, right there, average rate of change. Now, if we try to find the average rate of change between 2 different numbers, we're just going to have those 2 points. We just got 2 different points, 2 different values. So f of 6, when I plug in 6 in for x, what do I get for y? 18. When I plug in 2 for x, what do I get for y? 2. So 18 minus 2, and then divided by 4, and you get 4. Now, one more thing. Hopefully I have time for it. If you have to find the average rate of change from 1 to x. Okay, so all right, so x is your second point, right? We don't know what it is, so we're going to go ahead and we've got our equation here, so let's just go ahead and plug in that. F of x is 2x squared minus 3x, and then minus f of 1 is negative 1. Okay, so in our x minus 1, it just stays x minus 1. And that becomes 2x squared minus 3x plus 1 over x minus 1. Looks like we're going to have to factor, so that's going to be 2x minus 1, and then x minus 1. Doesn't matter which one goes first. X minus 1. Ooh, glad we factored, because boom, those cancel, and we've got 2x minus 1. That's the slope of the secant line, where the average rate of change is from 1 to x. Now, if I plug in for the next problem, if I'm finding using the same equation, if I'm finding the equation of a secant line containing these 2 points, well, 2 is now my x. So let me plug in this 2 here, 2 times 2 minus 1 is 3. So there we go. There's your slope.